Buckle up, it's space-time. Number 10. The WOW signal. On the night of August 15th, 1977, a volunteer astronomer named Jerry Ehman was sitting at his kitchen table in Ohio, scanning through paper printouts from Ohio State University's Big Ear radio telescope. The data was routine, the kind of background noise SETI researchers sifted through every day, hoping for something different. Then he saw it. He circled 6 characters on the printout and wrote a single word in red pen beside them. Wow. Big Ear had been scanning the sky near the constellation Sagittarius as part of a systematic search for extraterrestrial signals. Scientists had theorized that any intelligent civilization attempting interstellar contact would likely transmit at 1,420 megahertz, the frequency associated with neutral hydrogen, the most abundant element in the universe. It was considered the cosmic equivalent of a universal calling frequency. What Big Ear recorded that night fit that theory almost perfectly. The signal lasted 72 seconds, the maximum window the telescope could observe any single point in the sky before Earth's rotation carried it out of range. It was approximately 30 times stronger than the surrounding background noise, narrowband in exactly the way a focused transmission would be, and it bore every predicted hallmark of a non-terrestrial, non-solar system origin. Nothing in the data before or after it looked remotely similar. In the decades since, researchers have pointed telescopes at that same patch of sky more than 100 times. They have ruled out Earth-based interference, reflections from space debris, and passing comets. A 2024 study from the University of Puerto Rico proposed the signal may have been a natural hydrogen masher amplified by stellar activity near a red dwarf called Teegarden Star. But that explanation remains contested and unconfirmed by independent observation. Whatever produced that 72-second burst has been silent ever since. And the fact that the most carefully considered natural explanation still requires a chain of cosmic coincidences unlikely enough to leave astronomers genuinely uncomfortable tells you something important. The WOW signal has not been solved. It has merely been set aside. Number 9. The Lorimer burst. In 2007, astrophysicist Duncan Lorimer of West Virginia University handed his student a hard drive containing archival data from the Parkes Radio Telescope in New South Wales, Australia. The data had been sitting untouched for 6 years, collected in 2001 during a survey of the Magellanic Clouds. What the student found buried inside 480 hours of recordings was something nobody had ever seen before. A burst of radio energy so intense, so brief, and so impossibly far away that the scientific community initially refused to believe it was real. Radio astronomy had a framework for what strange signals looked like. Pulsars, the rapidly spinning remnants of collapsed stars, emitted rhythmic pulses on timescales of milliseconds to seconds. Interference from terrestrial sources was common and well understood, a signal from billions of light years outside our galaxy, carrying the energy equivalent of everything our sun radiates over several days, compressed into approximately 5 milliseconds, did not fit any existing framework. It was so anomalous that the first reaction from many researchers was to assume the instrument had malfunctioned. The burst, designated FRB 010724 and now known as the Lorimer burst, was real. It had traveled an estimated 1.5 to 3 billion light years before hitting the Parkes dish, and the dispersion of its radio frequencies across the journey confirmed its extragalactic origin beyond reasonable doubt. Today, several thousand fast radio bursts have been cataloged. Some repeat, some pulse with eerie regularity on 16-day cycles. Some appear only once and vanish completely, never to be detected from the same direction again. The leading explanation points to magnetars, neutron stars with extraordinarily powerful magnetic fields, releasing energy during violent crustal quakes. That model accounts for some observed bursts reasonably well. It does not account for all of them, particularly the ones that repeat with the kind of clockwork precision that makes astrophysicists pause and reconsider their assumptions. Something out there can release the sun's entire several-day energy output in the time it takes to blink, and after nearly 2 decades of searching across thousands of detected events, we still cannot say with certainty what it is. Number 8. The impossible pulsar. In early 2017, a team of astronomers led by Gianluca Israel of Rome's Astronomical Observatory published a discovery in the journal Science that stopped the astrophysics community mid-sentence. Using the European Space Agency's XMM Newton telescope and NASA's New Star Observatory, they had confirmed the nature of an object in the galaxy NGC 5907, located roughly 55 million light-years from Earth. It was a neutron star, a city-sized remnant of a collapsed stellar core, and it was doing something that the known laws of physics said was impossible. Neutron stars have a theoretical brightness ceiling called the Eddington limit. This is not a guideline or an approximation. It is a direct consequence of the balance between radiation pressure pushing outward and gravity pulling matter inward. Exceed it, and the radiation should blow the accreting material away before it can generate more energy. The object designated NGC 5907 ULX-1 was radiating at approximately 1,000 times its Eddington limit, pouring out the energy of tens of millions of suns from a body no larger than a major city. The neutron star's spin period had been accelerating for years, measured precisely between 2003 and 2014, as it decreased from 1.43 seconds to 1.13 seconds per rotation, indicating it was consuming enormous quantities of infalling matter. Standard accretion models could not explain the luminosity, even when accounting for geometric beaming of radiation. The best available explanation requires the star to possess an exotic multipolar magnetic field, unlike anything previously observed, one that partially shields accreting material from being blown away by its own radiation. Several other ultraluminous X-ray pulsars have since been confirmed in other galaxies. Each one exceeds its theoretical brightness limit by factors of hundreds to thousands. The growing catalog of these objects has made it impossible to dismiss NGC 5907 ULX-1 as an isolated anomaly. If a city-sized object can pour out the energy of tens of millions of suns without tearing itself apart, the question that follows is an uncomfortable one. How many other physical limits encoded in our textbooks are simply wrong? Number 7. The signal from nowhere. In September 2004, New Scientist magazine reported on something that had been quietly circulating among SETI researchers for months. A candidate signal detected through the SETI at Home project, using data from the Arecibo Observatory in Puerto Rico, had passed through multiple filters designed to eliminate interference. The signal, designated SHG-B02+14A, had been detected 3 separate times. It was broadcasting near 1,420 megahertz, the same hydrogen frequency that defines the cosmic contact band. It was coming from a region of sky between the constellations Pisces and Aries. And at that precise location, there is no known star. The SETI at Home project distributed radio telescope data to millions of home computers for analysis. An unprecedented pooling of processing power designed to catch exactly this kind of anomaly. Researchers, including Dan Wertheimer at the University of California, Berkeley, had been cautious in their assessment, noting the signal was faint and its behavior unusual. But faint was not the unsettling part. The unsettling part was the frequency drift. The signal appeared to be shifting in frequency over time in a way consistent with a transmitter that was accelerating or decelerating, as though it were mounted on something in motion. Natural radio sources at that frequency do not typically behave this way. The drift pattern was not consistent with known interstellar dispersive effects. The signal appeared 3 times from the same sourceless patch of sky, on a frequency reserved by International Agreement for Radio Astronomy, exhibiting behavior that would be expected of a moving transmitter. And then it was gone. Subsequent targeted observations of that sky position returned nothing. No peer-reviewed paper ever definitively explained it. SHG-B02+14A sits in an unusual category. Too statistically significant to dismiss easily, too faint and infrequent to confirm. Most scientists lean toward an undiscovered instrumental artifact or unusual interference propagation. But after 2 decades, no one has conclusively demonstrated that either. A signal that repeats, comes from empty space, and then stops is either the most tantalizing hint of contact ever recorded, or a gap in our physics we have not yet found a name for. Number 6. The candidate from next door. On April 29, 2019, the Parkes Radio Telescope in New South Wales, Australia pointed toward Proxima Centauri, the closest star to our Sun at just 4.2 light-years away, as part of a breakthrough listen monitoring campaign. The telescope gathered data for hours. That data was handed to a Berkeley undergraduate intern named Shane Smith, who began processing it months later. In late October 2020, he found something that the entire Breakthrough Listen team would spend the next year struggling to explain. a narrowband signal at precisely 982.002 megahertz, drifting slowly in frequency, present during every on-source observation and absent when the telescope pointed elsewhere. Breakthroughs. LISTEN had been scanning stars since 2015 without producing a single signal worthy of extended analysis. The project's filtering algorithms were specifically designed to eliminate radio frequency interference, earthly transmissions, satellite reflections, and known instrumental artifacts. Signal BLC1, as it was designated, passed through more of those filters than any candidate the project had ever encountered. Its frequency, 982 MHz, is a region of the radio spectrum with no known natural emitter and no commonly identified human source. Its drift rate suggested a transmitter experiencing Doppler shift, as one might expect from a body orbiting a star. The star had appeared to come from hosts at least one confirmed planet within its habitable zone. Proxima b, a rocky world roughly 1.3 times the mass of Earth, orbits within the distance range where liquid water could theoretically exist. The signal persisted for more than 2 hours across 5 separate 30-minute observations. When Sophia Sheikh at Penn State University led the subsequent detailed analysis, she described it as the most compelling candidate the project had seen. 2 papers published in Nature Astronomy in October 2021 concluded that BLC1 was most likely an unusual form of terrestrial interference, an intermodulation product of local electronic equipment drifting in a pattern that mimicked an astronomical signal. No redetection has occurred. No definitive terrestrial source has been conclusively identified. The nearest star to our Sun may host a habitable planet. Something in that direction was transmitting on a frequency nothing in nature should produce. The explanation that eventually satisfied the scientists was technically plausible but has never been directly confirmed, leaving BLC1 in a category that makes astronomers uncomfortable. Probably nothing, but not proven. Number 5. The clockwork of the galactic center. On the night of September 30th, 2002, the Very Large Array Radio Telescope in Socorro, New Mexico was conducting a monitoring survey of the galactic center, the dense and turbulent heart of the Milky Way. Over the following 7 hours, astronomer Scott Hyman of Sweetbriar College and his colleagues detected 5 bursts of radio energy emerging from a point source near the galactic center. The bursts were striking, not for their strength alone, but for their rhythm. Each one lasted approximately 10 minutes. Each one was separated from the next by exactly 77 minutes. They were identical in brightness. When the team finally published their findings in 2005, they gave the object the designation GCRTJ1745-3009, and they were candid about one thing: nothing like it had ever been seen before. The galactic center is among the most intensely studied regions of the sky. It hosts Sagittarius A star, the supermassive black hole at the heart of our galaxy, surrounded by dense clouds of gas, dust, supernova remnants, and exotic compact objects. Astronomers have cataloged thousands of radio sources there. Pulsars, which emit precisely timed pulses, do so on timescales of milliseconds to seconds, not 77 minutes. Magnetars flare unpredictably. Binary stars produce complex variability patterns that shift over time. Nothing in the established catalog of galactic radio behavior matched what the VLA had recorded. Additional detections followed in 2003 and 2004, but each subsequent burst was weaker and shorter than the 2002 events, as though the source were fading. Later archival searches found no confirmed detections of the object before the 2002 observations, despite the galactic center having been monitored at similar frequencies for years. Since 2004, GCRTJ1745-3009 has not been detected again, despite dedicated searches. Proposed explanations include a double neutron star binary system, a precessing pulsar, and a radio-emitting white dwarf. Each model accounts for some of the observed properties, and fails to account for others. The extraordinary precision of the 77-minute interval, refined to 77.012 minutes by later analysis, points toward a rotating or orbiting system, but no candidate object has been confirmed at the source position. Something near the heart of our galaxy was broadcasting on a precise 77-minute schedule, and then, without explanation, it went silent. Number 4. The black holes that shouldn't exist. At 3:02 UTC on May 21st, 2019, detectors at both LIGO facilities in the United States, located in Hanford, Washington, and Livingston, Louisiana, simultaneously registered a gravitational wave signal. So did the Virgo detector in Cassina, Italy. The signal lasted less than 1/10 of a second, resembling, as one LIGO scientist described it, not the long rising chirp of a typical merger, but a single sharp bang. When the LIGO-Virgo collaboration worked backward through the waveform data to reconstruct the source, they arrived at a result they had not anticipated and could not easily explain. A collision of two black holes that, by all the rules of stellar physics, could not have existed. The pair instability mass gap is not a hypothesis. It is a direct prediction of nuclear astrophysics, the consequence of what happens inside a star between roughly 65 and 120 times the mass of the Sun. At those masses, the star's core produces electron-positron pairs that reduce the radiation pressure supporting it, triggering a catastrophic instability that completely destroys the star in a thermonuclear explosion. No remnant black hole forms. The gap is considered one of the cleaner predictions in stellar evolution theory, tested repeatedly against population studies of compact objects. The two black holes that produced GW 190521 had masses of approximately 85 and 66 solar masses. Both fall squarely inside the forbidden zone. Their merger produced a remnant of approximately 142 solar masses, the first confirmed intermediate mass black hole ever detected. The gravitational wave signal traveled roughly billions of light years to reach Earth. A possible optical flare detected by the Zwicky transient facility in the same sky region at the same moment was never conclusively confirmed as a counterpart. The most likely explanations involve second-generation mergers, black holes that formed not from collapsing stars, but from earlier collisions of smaller black holes in dense stellar environments, or unusual stellar mergers that bypass the instability entirely. None of these scenarios is easily produced by standard stellar population models. The probability that the primary black hole formed through normal stellar collapse was calculated at 0.32%. Two objects that should have been erased by physics merged to create something that the universe technically should not have allowed, and what that tells us about the stars we have yet to observe is a question astrophysics has not finished answering. Number 3. The universe's first light was too cold. On February 28, 2018, the journal Nature published a paper that unsettled cosmologists in a way that purely theoretical debates rarely do. Judd Bowman, an astronomer at Arizona State University, and his team at the experiment to detect the global epoch of reionization signature operating a compact radio antenna array at the Murchison Radio Astronomy Observatory in Western Australia, reported a detection. They had found the faint imprint of the universe's cosmic dawn, the moment approximately 180 million years after the Big Bang, when the first stars ignited and began heating the surrounding hydrogen gas. It was the earliest direct signal ever detected from our universe's history, apart from the cosmic microwave background itself. The signal was real, and it was wrong. The 21-centimeter hydrogen signal from this era encodes the temperature difference between the primordial hydrogen gas and the cosmic microwave background radiation bathing it. Standard cosmological models placed firm limits on how large that temperature difference could be. The physics was well established. The gas simply could not cool below a certain floor set by its gravitational and radiative history. When Bowman's team measured the signal, centered at 78 megahertz and approximately 0.5 Kelvin deep, the depth was more than twice the maximum the standard model allowed. To explain a signal twice as deep as physics permits, something had to be removing energy from the primordial hydrogen gas beyond what ordinary cosmic expansion could account for. The most prominent explanation, proposed by theorist Renan Barkana of Tel Aviv University within weeks of the announcement, suggested that cold dark matter particles were interacting directly with hydrogen atoms, draining heat from the gas through a mechanism our particle physics models do not currently include. An alternative explanation proposed the existence of an unknown radio background brighter than the cosmic microwave background in the early universe, implying an entire population of energetic sources from the first 180 million years of cosmic history that we have entirely missed. The status of the detection itself has become contested. A 2022 paper using the CERES-3 experiment in India challenged the Bowman team's measurements, rejecting their best-fitting signal profile at high statistical confidence. The debate over whether the anomalous depth is genuine or an instrumental artifact continues in the peer-reviewed literature without resolution. Whether the anomalous signal holds up or not, The universe has presented us with a question we cannot yet answer. The first chapter of cosmic history may contain physics we have not written, and the first light from the first stars may be carrying a message about the nature of dark matter that we have not yet learned to read. Number 2, the universe has a preferred direction, and it points at us. In 2003, the WMAP satellite delivered what was supposed to be the definitive map of the cosmic microwave background, the faint thermal afterglow of the Big Bang itself. It was the oldest light in the universe, imprinted 380,000 years after creation, carrying within its temperature fluctuations the seeds of every galaxy, every star, and every atom of matter we can observe. The map confirmed the standard model of cosmology in extraordinary detail at small scales. Then scientists examined the large-scale structure, the gentlest, broadest ripples across the entire observable universe, and they found something that the theory explicitly forbade. The standard model of cosmology requires the universe to be isotropic, meaning it has no preferred direction. At the largest scales, it should look statistically identical, regardless of where you point your telescope. The quadrupole and octupole moments of the cosmic microwave background, the largest observable ripples in the oldest light, are not random. They are aligned with each other, and they are aligned with the plane of Earth's orbit around the Sun. Cosmologists Kate Land and João Magajo of Imperial College London named this the axis of evil in a 2005 paper, a name chosen to reflect exactly how troubling the alignment was for the foundational assumptions of their field. The ESA's Planck satellite, a more precise and capable instrument, confirmed the anomaly in 2013, and again in 2015 with better data. The alignment remained. A second anomaly in the CMB, a large cold region in the constellation Eridanus roughly 500 million light-years across, and significantly colder than its surroundings, has never been explained by standard cosmology either. The two anomalies together form a pattern. The universe, at its largest and oldest observable scales, appears to be structured in a way that involves the position of our solar system. The possible explanations are all uncomfortable. The first is a systematic error in every space telescope that has examined the CMB, an option that has been tested exhaustively and never confirmed. The second is a profound statistical fluke so improbable it strains credibility. The third is that our cosmological model, built on the assumption of isotropy, is missing something fundamental about the shape, topology, or origin of the universe itself. The oldest light in the universe knows which direction Earth orbits the Sun, and we do not yet have an explanation for that which does not require rewriting the foundations of cosmology. Number 1. The universe is expanding at two different speeds simultaneously. In 1998, astronomers expected to measure something straightforward, the rate at which cosmic expansion was slowing down due to gravity. Two independent teams, one led by Saul Perlmutter and one led by Brian Schmidt and Adam Riess, set out to make that measurement using Type 1a supernovae as cosmic distance markers. What they found instead was so unexpected that all three men were awarded the Nobel Prize in Physics in 2011 for their refusal to dismiss the result. The expansion was not slowing. It was accelerating. Something was pushing the universe apart with increasing force, a discovery that revealed that 68% of the entire universe consists of something we have never directly detected, which we call dark energy, for lack of a better name. Measuring the precise rate of that expansion, the Hubble constant, became one of the central projects of modern cosmology. Two fundamentally independent methods were developed. The first measures the cosmic microwave background, the oldest observable relic of the Big Bang, using the physics of the early universe to infer the expansion rate. The Planck satellite team produced a value of 67.4 kilometers per second per megaparsec. The second method uses Cepheid variable stars and Type 1a supernova as a distance ladder across the nearby universe, measuring expansion directly. Adam Riess and the SH0ES collaboration at Johns Hopkins University and the Space Telescope Science Institute produced a value of 73.0 kilometers per second per megaparsec. These two numbers describe the same universe. They cannot both be right, and yet every attempt to find an error in either measurement has failed. The discrepancy has been independently confirmed by gravitational lensing time delays through the H0 LICO project, by measurements of the tip of the red giant branch, and by gravitational wave standard sirens. Each new method has refined the values rather than resolved the conflict. When the James Webb Space Telescope came online and Rees's team reran their sifted measurements with its superior resolution in 2023, the tension did not shrink, it held. The statistical significance of the disagreement has crossed 5 sigma, the threshold scientists use to declare discovery certain, meaning the probability that this conflict is a random fluctuation in the data is less than 1 in a million. Every systematic error that could explain the discrepancy has been identified, tested, and ruled out by multiple independent teams using different telescopes, different stars, different methods, and different assumptions. The tension is real. The implication is either that the early universe and the late universe obey different physics, which is by definition impossible in a consistent theory, or that something fundamental is missing from our standard model entirely. The leading candidates include new particles that decayed shortly after the Big Bang, modifying the early universe measurement, a form of dark energy that changes in strength over time, modifying the late universe measurement, or modifications to general relativity itself on cosmic scales. None has been confirmed. All of them, if true, would require rebuilding significant portions of physics from the ground up. We have spent a century learning to read the one number that describes how everything in the universe is moving apart. That number now gives us 2 different answers simultaneously, both of them confirmed to the highest standard of scientific certainty, both of them precise, both of them derived from real data by the best minds in the field. The universe is not broken. Our understanding of it is. And the most haunting part is not the gap between 2 measurements. It is what that gap means. Somewhere between the birth of the cosmos and the present moment, something happened that our physics cannot see, cannot name, and cannot explain. And every new telescope we build makes the silence around that question louder. If you want to see more videos like this, click the video on screen now and make sure to subscribe.